this video, I want to talk about the use of free body diagrams and kinematic diagrams as a tool to help us solve dynamic problems. So free body diagrams should hopefully be relatively familiar from anyone who's done any coursework in statics, in that a free body diagram is used to collect graphically everything that is going on in a system. So if we have a system that's subject to forces, maybe things coming into contact with other objects or interactions with the ground, we would usually draw an imaginary box around that thing in order to separate it from everything else, and then any of those interactions become forces. And we can also have directly applied forces as well. So if we have a box sitting on the ground, and I want to push on that box with a force, I can separate this out as a free body diagram by grabbing, that's a little oddly shaped, by grabbing the box itself, saying, okay, I'm pushing on it with a force. I am removing that interaction with the ground, which means there must be some sort of force in response or that replaces it, a normal force in this example. And the box presumably has mass, which means that I'm going to have some sort of weight, which is the mass of the object times gravity, acting on that, usually applied at its center of gravity when it comes to a free body diagram. And when we think about Newton's second law, we have, in a planar case, we have sum of forces in the x, sum of forces in the y, and the summation of moments. And this free body diagram represents the left-hand side of these equations. So the forces and any moments that I may have, this force doesn't look like it's acting through the center of gravity, which means it's going to produce a moment around the center of gravity. So anything like that is represented by the left-hand side of this equation, and it's shown on the free body diagram. Now, if we want to have a graphical representation of the right-hand side of this equation, we could set this equal to, graphically speaking, a kinematic diagram. And the kinematic diagram is effectively the same thing as the free body diagram, except that instead of applying forces and moments and such and torques to the object, we're going to try to designate how it moves. So in this case, I might say, well, I have some forces pushing on this, and it is going to move to the right-hand side. I have the possibility of some rotation, and I suppose in theory I could draw an arrow on here to indicate possible acceleration in the vertical or y-axis direction. However, from our problem, if this thing has mass and it's constrained from moving up and down by the floor, or from moving down, I guess, by the floor, then likely the acceleration in the y is 0 in terms of it actually moving, right? Of course, we have gravity, but the gravity is represented in this case by the weight of the object. So as a net result, we could probably leave that off, but for completeness, I'll put it on there. So we can take the free body diagram that we're probably familiar with, set it equal to the kinematic diagram, and use it as a graphical tool to help us visualize everything that should be showing up in our equations of motion, which form the basis for Newton's second law. So for this problem, we would end up seeing that, okay, we have a summation of forces in the x, which gives us the the force that we've applied, F, and it's equal to that mass times the acceleration in the X. Summation of forces in the Y, we have this normal force due to the ground reaction minus the mass times gravity, or the weight, however you want to represent that, equal to MAY. However, given the constraints, we can say that this is going to be 0. And we potentially have a summation of moments. Now, I didn't specify any distance here, but we have our force times our distance to the center of gravity, whatever that distance ends up being. And that is going to be equal to I alpha. So I could go through then, assuming I actually had some numbers, and solve these equations. And again, the free body diagram and the kinematic diagram are just tools that we're using to graphically represent what's going on in this system. All right, thank you.